These are the solutions for the chi-squared review problems. Number one, we have a situation where we have three different examiners named A, B, and C, and they are giving exams, and the results of the exams are either credit, pass, or fail. And we are going to analyze whether or not some of these examiners are easier or harder grader than others by seeing if there's a relationship between the percentage of credit pass fail compared to which examiner is giving them. So basically we're going to do a chi-squared test on the relationship between exam results and which examiner is doing the exam. So first, state the null hypothesis H0 for this data, and basically we're just going to say that one thing is independent of the other. That's what you always say with the null hypothesis. You say that A is independent from B. So what's A? Well, let's say A is the result of the examination, and we're going to say it's independent of who is the examiner. Okay, so the null hypothesis, we always assume that they're independent. Okay, B, write down the number of degrees of freedom. Well, in this case, it's a little bit different than the book problems because the book problems usually give you a table. And in this case, they describe the table, but they don't actually give it. So if you were going to draw the table, you would draw that the examiners A, B, C are either, over here, or maybe you would put them here. And then the other would be credit, pass, fail. So I decided to put credit, pass, fail on the left side. I decided to put the examiners across the top. So that's the way mine looks. Either way you decide, you're going to have a 3x3 table here, okay? And remember that whenever you want to figure out the degrees of freedom, what you're doing is you're figuring out how many of these cells can actually be chosen by you and how many of them are going to be calculated. And remember that if you have a 3x3 table, then you can pick the 2x2 table. You can choose these values, but once you choose these four values, then the third value in each row and column must be calculated because you've already chosen the first two. The third one can't be chosen. It has to total up to be these subtotals. So we know that the degree of freedom must be 4 in this case, which would be 3 minus 1 times 3 minus 1, or a 2x2 table. So a 2x2 table has 4 degrees of freedom. So of the 135 students who sit the exam, 30 get credit and 45 are tested by examiner A. So, in the book problems, we always had subtotals for every single row and column. In this case, they're not giving you all the data because you don't really need it for this problem. So the 45 would be the subtotal for the A column. 30 is the subtotal for the C, the credit row. And so we just put those subtotals here. And the total for, all the students would be 135. So we want to calculate the expected number of students who get credit and are tested by examiner A. So that would be specifically this cell right here. And remember that the way you calculate the expected frequency for this cell would be to find the percentage of this column, find the percentage of this column, multiply them together, and then multiply times the total. So for the A column, the percentage would be 45 divided by 135. The credit row, the percentage would be 30 divided by the total of 135. And then you would multiply the two percentages times the total number of students. Okay, so you get 45 times 30 divided by 135 divided by 135 times 135, and it's equal to 10. So the expected number of students who get credit and are tested by examiner A would be 10. Okay. Using a 5% level of significance, the p-value is found to be 0.0327, correct to 3 significant figures. State whether the null hypothesis should be accepted. Justify your answer. Okay, so we have a p-value that is less than the level of significance, which is 5%. Remember, 5% is 0.05, it's not 0.5. Okay, so the p-value is still less than 0.05. When the p-value is less than the significance level, then we reject the null hypothesis. Okay, so that's just the rule. Okay, you have to memorize that. Uh, Maybe what's easier to remember is that when the chi-squared value is more than the critical value, we reject the null hypothesis. Maybe that's easier to remember because of the, you remember what the exploration we did at the beginning, and we defined that the chi-squared is actually an indicator of dependence. So the bigger it gets, the more dependent um, your distribution is. So when the chi-squared is equal to 0, that means that it's totally independent, so the null hypothesis is true. Okay, and so once you figure out that the chi-squared value is really big, then you know that the distribution is dependent and the null hypothesis should be rejected. Okay, so the two rules for rejecting the null hypothesis are if the p-value is small, if it's less than the significance level, we reject the null hypothesis. Or if the chi-squared value is big, if it's more than the critical value, we reject the null hypothesis. And remember, the chi-squared value is always compared to the critical value, and the p-value is always compared to the significance level. Okay, so those are two different things, significance level and critical value, but they're both related, because at the exact moment that the p-value becomes less than the significance level, the chi-squared value becomes more than the critical value. So those two values are the dividing border between independence and dependence. So you have independent distributions, you have dependent distributions. The null hypothesis always says that the distribution is independent. The alternative hypothesis, which is represented by H1, says that the distribution is dependent, or there is a relationship between the two factors. Okay, and in the case that the alternative hypothesis is true, of course, the null hypothesis is rejected. Okay, so when do you reject the null hypothesis? Well, when chi-squared is really big, it's so big that it's larger than the critical value, you reject the null hypothesis. When the p-value is small, when it's so small that it's smaller than the significance level, then you reject the null hypothesis. Okay. So remember that when you have a totally independent table, then chi-squared is equal to 0 and the p-value is equal to 1. So if you get something really close to that, you've probably made a mistake and you entered the expected frequency table into your calculator instead of the table that you intended to put in. Okay, so you know your results, if you get chi-squared equals 0 or something close to 0, something really small, or if you get p-value equal to 1 or something really close to 1, then probably you put the wrong thing in your calculator or you're looking in the wrong table. Okay. So I don't remember if I got to the end of this, so just recapping. Since the p-value that you got, and in this case they just gave you the p-value, they just want to see if you know what that means. So if the p-value is small, that means you reject the null hypothesis. Well, this is small, but is it really small? Well, what do we compare it to? Well, we compare it to the significance level, which in this case they say let's use 5%. 5% is 0.05. So is it smaller than 0.5%? Yes, it is. So then we reject the null hypothesis. Now, what if they had said using the 1% level of significance? In that case, do you reject the null hypothesis? No, because 0.0327 is not less than 0.01. So depending on what significance level you choose, in this case, you might reject the null hypothesis and you might not reject the null hypothesis. So since we do reject it in this case, that means that there is a relationship between the examiner and the exam results, so there is some bias here. Okay, so number 2. Tom performs a chi-squared test to see if there's any association between time to prepare for a penalty kick and the outcome is related. And so, and Tom is performing this test at the 10% level. Now, whenever they give you the statistics here, you're not supposed to do anything with it yet. You're going to use it later. Okay? So basically the two factors are, how much time does the penalty kicker use to psych himself up to make the goal, and whether or not the goal was made or not. So I'm going to put across the top how much time the kicker spent preparing short, medium, long, and then across the side I'm going to put whether he made the goal or no goal. So the null hypothesis is that the two factors are independent. So the penalty kick outcome is independent of the preparation time. We always assume that it's independent for the null hypothesis. Find the number of degrees of freedom for this test. Well, remember, for a 2 by 3 table here, there's only two cells that you can choose before you have to start calculating, which is this cell and this cell. After you calculate this cell and this cell, the third cell, you have to calculate it, right? And then the same thing with these, the second row. Once you have the top row, you can't choose the bottom row values. And I kind of highlighted the ones you can choose, which would be like these first two cells. So basically, the degrees of freedom would be 2. If you want to calculate that, if they ask you how you calculate that, you would say, well, I take the number of rows, I subtract 1, I take the number of columns, I subtract 1, and I multiply the two times each other. So 2 minus 1 times 3 minus 1 gives us 2. Okay? The p-value for this test is 0.073. What conclusion can Tom make? Justify your answer. Okay, so here they're just giving you the p-value again. So like when you did the book problems, you actually calculated the p-value using your calculator. In this case, they're already giving it to you. They're just saying, how do you interpret it? Well, the p-value, if it's 0.073, you're going to compare it to the significance level. Here at the top, they told us the significance level is 10%, which in decimal is 0.10 or 0.10. Okay, so is 0.073 less than 0.10? Yeah, it is. So remember that when the p-value is less than the significance level, we'll go back to number 1. So if the p-value is smaller than the significance level, we reject the null hypothesis. It's dependent. So that's what we do here. We're going to reject the null hypothesis, and penalty kick result is related to the prep time. So however long, if you spend, more time to psych yourself up, maybe the penalty kick has, a higher percentage of goals or whatever. Okay. Number 3. Maybe we could do half of this one. Tony wants to carry out a chi-square test to determine whether or not a person's choice of one of the 3 professions, engineering, medicine, or law, is influenced by gender. Okay, so in this case, we're going to make a table. And the reason why we're making this table is to make it easier to picture the rest of the problem. Even though they don't ask for the table, it helps to draw this table because then it looks more like the problems that you did in the book. So the 3 professions are engineering, medicine, and law. And so we'll put those across the top. And the gender is male, female. We'll put those on the side. And then basically when we say the null hypothesis, we're just going to say that profession is independent of gender because those are 2 factors. And in the null hypothesis, you always assume that they're independent. Okay. Write down the number of degrees of freedom. Well, by looking at this 2 by 3 table, we know that we can choose these 2 values and these 4 values we have to calculate. But if you want to put it in terms of a math rule, you say that the number of rows minus 1 times the number of columns minus 1 multiplied together is going to give you 2, right? So that's how you get, using a math rule, that those are 2. So degrees of freedom is 2. Of the 400 people interviewed, 220 were male and 180 were female. So they gave us the subtotals for male and female. We write them down here. Total for all students is 400. And then they tell us that 80 of the people, that was men and women, chose engineering, so we put 80 in the engineering column. We don't know what these 2 columns are, but we don't need to know, because they never ask us anything about that. Calculate the expected number of female engineers. So to find the number of female engineers, we would need to multiply the percentage of this column times the percentage of this row, and then multiply times 400 total. So the percentage of this column would be 80 over 400. The percentage of this row would be 220. I'm sorry, we're supposed to do it for female engineers, so it would be this row. So it would be 180 divided by 400 for females, 80 divided by 400 for engineers. So if 80 out of 400 of the people were engineers, and if 180 out of the 400 people were female, how many are female engineers? Well, in that case, you're going to say, oh, well, I'm going to multiply this percentage times this percentage, and that'll give me the percentage of female engineers. And, of course, that may or may not be true. If it's an independent distribution, then that's what you're going to get. So that's what we're calculating here. The expected number of female engineers if it is a independent distribution, and I will continue in the next